Welcome students on today's lecture of circular tank with fixed base. Okay, in the previous lecture we have already computed the reinforcement details for the base slab, for the walls, for both outer face and the water face. So today we will discuss about the detailing of the circular water tank. So we'll just go through what all has been done. So this was the question wherein the capacity was 4 lakh liters. The capacity was 4 lakh liters and the depth of the water was 4 meter, free for 200 mm. Density of water 9.81 kilo per meter cube. The stress in concrete was given as 1.2 Newton per mm square. Stress in steel 100 Newton per mm square. This is what we have decided. So the diameter of the circular water tank worked out to be 11.5 meter. The height of the wall was 4.2 meter. The thickness of wall and thickness of base slab was taken as 200 mm. So further, we computed the bending moment, ring tension and ring shear according to the code book. So let us see. So according to the code book, according to the clause number 3.1. So let us go there. So this was the condition for which we have solved, that is cylindrical tanks with circular tank and ring tension and movement in the wall. So our condition was wall with fixed base, free top and subjected to triangular load. So according to this was the diagram, and here you can see the ring tension at various height of the wall of a cylindrical tank fixed at the base and free at the top subjected to a triangular load are given in table number 9. Okay, then the bending moment in a cylindrical wall fixed at the base, free at top and subjected to the triangular load are given in table number 10. And the shear at the base is calculated by this coefficient for shear at the base of a cylindrical wall given in table number 11. So we used this. So let us go to these tables 9, 10 and 11. So you can see here, so this is table number 9 now. In this we get the ring tension and this is the tension coefficient. So tension is equal to coefficient into W H into R. This is for circular water tank with fixed base, free top and triangular load. So we have to calculate h square divided by dt, which was computed here. You can see h square divided by dt worked out to be 8. So in this, so h square divided by dt is 8 here. Okay, and we computed from 0.6h from the top. So the value worked out to be 0.575 plus indicates it is tensile. Here you can see positive sign indicates it is tension. So this value plus 0.575 was substituted here, and W is the density 9.81. H is the height of the wall, that is 4.2, and R is the radius. So we get the ring tension. So you can see here, I will just show it to you. So tension, ring tension worked out to be 148.069 kilonewton. Then in the next table, we computed the bending moment. So you can see this is movement, table number 10. So bending moment in cylindrical wall fixed base, free at top and subjected to triangular load. So bending moment is equal to coefficient into omega h cube kg meter per meter. So we already know h square divided by dt was 0.8. So this is 0.8. You can see, and moment for 1h it got to be minus 0.0146. So this value minus 0.0146 was substituted here, and omega is 9.81 and h is 4.2 cube was computed. You can see here. So here you can see maximum bending moment coefficient minus 0.0146 into 9.81 into 4.2 cube will work out to be 10.61 kilonewton meter. Then next we computed the shear at the base. So you can see the shear at the base for triangular is WH square. So h square divided by dt is 8 here. So let us see here. So h square divided by dt is 8, and for triangular load it was plus 0.174. So we substitute the coefficient here. So you can see here it is computed 0.174 into 9.82 into 4.2 square, which is working out to be 30.11 kilonewton. So this was the maximum shear. So then we did the design of section. So in the design of section, we came across the steel for bending moment. The depth was done with a 200 mm thickness with effective power of 40 mm. Then steel for bending moment, providing 16 mm diameter at 300 mm center to center as vertical reinforcement on the water side, on the water face. Similarly, for hoop tension, so providing 12 mm diameter at 75 mm center to center at hoop reinforcement on the water face. And chuck was also done, and minimum distribution steel was provided 8 mm diameter at 100 mm center to center as vertical and horizontal distribution on the outer face of the wall. Then we designed the base slab, which is of thickness 200 mm and which rests on a firm ground. So minimum AST, so we provided 8 mm diameter bars at 200 mm center to center as vertical and horizontal distribution on the outer face. Shear stress was checked and it was safe. So the main part today we will discuss is the reinforcement. So this is how the reinforcement, this is the half section which we have provided. So let us see how it is done. So you can see here, this is the reinforcement provided. So this whatever water tank is there, that is cut section. So this is half we have to cut, and this is one of the wall. So here inside the water will be stored, and here it is outside. So this reinforcement is under the inside the water face, and this reinforcement is outer the water face, and this is the base layer. Now this is a reinforcement detail in circular tank with fixed at base. So let us see the dimension first. So that at total height of the wall is 4.2 meter. So depth of the base slab is 2 meter, 200 mm, and width of the base slab is 200 mm. Now let us see the reinforcement. So first we'll start with the reinforcement on the water face. So this is the water face. So you can see the main reinforcement is provided at 12 mm phi at 400 mm center to center on both the faces. Okay, that is this. That is it for ring. And this is 12 mm diameter at 200 mm center to center, and this is 20 mm phi at 200 mm center to center, and this is 12 mm phi at 130 mm center to center, and this whatever bar is curted, this is 8 mm diameter at 200 mm center to center on both the faces. Now let us see the reinforcement on the outer face. So here at this it is 12 mm phi at 400 mm center to center rings. Here it is 12 mm at 200 mm center to center. Here the spacing is made less, and here the spacing is made more. The reason behind it is because the hoop tension will act here. That is the reason why here the spacing is less, so that it provides more stability as well as strength. So this reinforcement, the bar will go in this fashion and it will get curtailed here, and this will go in this fashion and this will go inside here. Then this is nothing but RCC slab itself. So here also on both the faces, that is inner and outer or water or outer face, 8 mm diameter bars 200 mm center center is provided. That means these are 8 mm diameter bars at 200 mm center center. Even this bar is 800 mm, 8 mm diameter bars at 200 mm center to center. So this is how the reinforcement details for the circular water tank with the fixed basis. So we can refer this only for the drawing. So you can note it down. So this completes the design of circular water tank with fixed base, free top, and subjected to triangular load. So this is done according to IS 3370 part. So this is the end of the design. You can note down the reinforcement and you can solve the numerical. Thank you.